Good morning, dear. Welcome back. So today we have machine learning lecture number 8, where we are going to discuss the normal equation in matrix form. So just a recapitulation, you have seen that we are trying to design hypothesis or predictor from the given data. Okay. Incidentally, this data are called label data because take the example of housing price data. Housing price is labeled with some features, right? Let it be floor area, or it could be many other things. For example, this feature could be many. Okay, number of rooms, number of stories, how old the house is, locality of the house. For example, house price is also depends on the locality, the convenience of public transport, children's school, all kind of marketplace. So that's also, so it's really complex, right? So when these features are very large, we still have data we call label data because corresponding to each features. A typical example you can see from the data set which we have, I think, Windsor City of Canada. That also contains several features. Okay, so these are the example of label data and how we are actually designing the hypothesis. The process, linear regression process, is also called actually supervised learning method. Okay, we are using supervised learning method because we are telling hypothesis that okay, if this is the feature, this would be the price. If this is a feature value, this would be the price. So incidentally, this is supervised learning and label data. Now, as you can see, question may arise or normal equation in matrix form. Why we need to write? We need to write because for practical problem solving, when n is really large, maybe 10, 100, maybe 1000, okay. Some examples, it could be many, of course, more than 1000 or some values, 10,000 maybe up maximum. Beyond that, this methodology may not work, so we need to study another methodology. Because there could be, in this big data era, there could be many more features. Like we have 1.4 billion people, and some aspects, if you try to collect data of 1.3 billion people, they might have several features which is related to particular objective. For example, calculating the GDP or kind of thing. They are really complex. So when n is large, then hypothesis will look like this. You see, this hypothesis parameters by W. This x is in vector form. If I write, then this is equals to W0, x0, W1, x1, W2, x2. So x1, x2, x3 up to xn, these are the features. And each feature is associated with our parameter. Okay. Incidentally, this first term is interesting one. It is known as bias, or sometimes it is called also threshold. This is not feature. Okay, but still, that's why normally x0 we put value, we put 1. Still we want to attach a parameter W0 because it has advantage. For example, with our earlier example, say this is x. Okay, and if our x was something like this, okay, simple like this. But if this term is not there, so it has a purpose, then my predictor line would be like this. Okay, which is not good because I am constraining my predictor to pass through the origin. Okay. On the contrary, if we have this parameter and we also evaluate or calculate the parameter from regression analysis, then parameter will have some value which actually realistically will design the hypothesis. So it could be like this, it could be like this, it could be like this, depending on what value of W0 is taken by the data. Okay. So that's the idea. So henceforth we call it bias or threshold, but it plays an important role. So now if we consider m number of samples, okay, then what is going to happen? I can rewrite the hypothesis for each sample. Okay, this is sample number 1, sample number 2, up to n. So we have m number of samples. But interestingly, this part, W1, W0, W1, W2, those parameters, they are not, they are attached with feature which depends on sample. Okay. This is not. Okay. Then in vector form, in matrix form, if we write that y, that is the actual value of predictor, will have m cross 1, isn't it? Dimension. H also will have m cross 1 dimension. And this we are trying to write in vector form. This is where x bar has a dimension, this is a matrix, has a dimension m cross n plus 1. Matrix, vector, these are all known to you. I am using them. Okay, vector, matrix, basically they are the same. Vector is the column matrix normally. Okay, so it has only one column. Okay, but here is a matrix. X bar is defined like this. Okay, these are with sample x0, 1, x1, 1. This is corresponding to first row, corresponding to sample number 1. Second row corresponds to, these are the feature rows, okay, correspond to sample number 2, like that. So, so it has in the range space dimension is m cross n plus 1, because x0 is there, n features are there, with x0 is n plus 1, and m is the number of samples. So this can be written like m cross n plus 1. Okay, and we have defined in vector form w equals to w0, w1, w2 up to wn. So its dimension is n plus 1 cross 1, and it belongs to the range space n plus 1. And x also can be written, defined like this: x0, x1, x2 up to xn, dimension, having dimension this. So basically, x bar matrix is the transpose of this expressed for each sample. As simple as this. Is it clear? Yeah? I believe it is clear. Now, let us call it equation number 2. Then let us try to write the cost function Jw equals to 1 by 2m. 1 by 2m, as I have told you, this is for mathematical convenience, okay? Because this function will be differentiated, which has a square here. So basically, this 2 and this 2 will cancel out, and m is the number of samples, is the constant term. So it will simplify that expression. That's the reason it is there, otherwise there is no reason. Okay. So from equation 2, the hypothesis in vector form can be written like this. Okay. HWX dimension is m cross 1 equals to x bar, is dimension of course is m cross m plus 1. Okay. So you can check the dimensions correct. Times w n plus 1 cross 1. Okay. So now a little linear algebra. So JW in this vector notation, with this vector notation, this will take the shape of this. Okay. So this is square. So suppose this is x square. I can always write it like this. Okay. This can be always written like this. And exactly we are doing that. We are writing this square term transpose x bar w minus y. Okay. Y is the level. Transpose times x bar w minus y. Okay. And now just simplification. So this transpose is coming over here times this, the x transpose w, this transpose, so minus multiplied by y, minus y transpose times this term, here I have written, and then y transpose minus plus this term I have written. Okay. And this is actually can be rewritten as long as their dimensions are allowing. We can always commute these terms because this is not cross product. Okay. So whimsically, as per our need, I have taken w transpose, w here, x bar transpose times x bar, and you can check their dimensionality, right? Always it should be same as it will satisfy this equation. Okay. And this is very interesting, and I am writing as per the convenience. This and this term are same. Okay. I can just show it here. Maybe it's a good exercise for you. Just very simple, right? You write the dimensions, x bar m cross n plus 1, this n plus 1 into 1 transpose of this, times y has m cross 1. So total it will be quantity, okay, 1 cross 1. Just check it. Then here also you have that m cross 1 transpose times x bar has m cross n plus 1 and w is n plus 1 cross 1. So I mean you are with me, and just here you can just somewhere take a notebook and do it. Very fun. Okay. And I can do this. Okay. This and this are same because quantity, you see, this, they are the quantity and their dimensions are matching. So I can write this as minus 2 x bar w transpose into y plus this term. Clear? Now, same old story what we did with our normal equation with only one feature. Now we are extending the same thing. Only thing is that we'll have to differentiate it with respect to a vector. Okay? So we are differentiating this cost function with respect to vector w, making it to 0 for optimization. That eventually will give me a condition from where we will calculate w. Okay, so let us try to do that. Very simple. So this is the expression. So I am differentiating this term with respect to w, this term with respect to w, this term with respect to w. So you should not be nervous because differentiating with respect to vector is similar to what differentiating with respect to a scalar. So this I can consider w square, okay, or x, if I put in this x, this is x square, and differentiating with respect to x will be 2x. Okay, so here also 2 double. Okay, so this part is differentiated, and then there is no parameter here, so it remains as it is. Very simple calculus. Okay, and here let us see, 2 is here and W transpose, just like W transpose as W, we can just differentiate it. So 2x bar transpose times y, and since there is no parameter here, constant term, it is 0. So eventually it is giving you W times x bar transpose, x bar equals to x bar transpose y, which now I am trying to take this guy in this on this side, so I am just multiplying it by its inverse. So this is becoming y, okay, and this is what taking this step. This is very, very important. This is what actually we are wanting. Okay, so W in vector form is equals to x bar transpose times x bar, inversion of that. Okay, times x transpose into y. Y is the level. Okay, so that's great. Okay, so whenever you can actually take the housing price data of a Canadian Windsor city, which we have on our site, and we will formulate some problem and we will solve it very quickly. You can solve it. Okay, and that's the beauty. This is in fact this is analytical formula, and we love analytical formula when there is no iteration, all kind of thing. This is not algorithmic way. But wait a minute, when I say I should be very precise, when I am telling there is no iteration, no algorithmic, this is not an algorithmic method, I must tell you that this matrix inversion is problematic. So advantage is analytical solution, we love it, okay? Very quickly the solutions can be obtained. Okay? And you see, these are linear simultaneous equation, and as you can see, there are methods for solving such linear simultaneous equations. One of the very popular method is Gauss elimination method, and Gauss elimination method has the computational complexity of inverting this matrix is of the order of n cube, which is not good at all, where n is the dimension of the matrix. Well, people have tried that, okay, can you reduce it? There is a algorithm called Prassen's matrix inversion algorithm. I hope it is visible. Prassen's matrix inversion algorithm, it has the complexity of the order of n to the power log 7 to the base 2. So it is somehow like 2.78. Well, it reduced a little bit, but still computational complexity is a problem. Another great problem is, I think that is the biggest problem, that for inverting this you need to assure that determinant of this matrix should not be 0, okay? Because determinant is the process of inversion of the matrix, you know, that adjoint by delta. Delta is the determinant of this matrix. If the determinant of this matrix x bar transpose times x bar is 0, then inversion will not exist. And when it could be 0, and if you have, you see, when a matrix is not of full rank, that means What is the meaning of this statement? That matrix is not a full rank. That means either is row or column are dependent. Okay, there are redundant. There could be redundant rows, redundant columns. Any of the thing, if it happens, then determinant will be 0, and you cannot find the inversion. And when it can happen in actual data collection, means okay, some entries are there. Say you have 1,000 entries in the matrix, and somehow some value which you are considering, they are redundant, means they are repetitive in nature, or some multiplication of one row or one column, that is they are redundant. Then that is the hidden enemy that will make this matrix non-invertible. Okay, so that's the biggest problem, and you need to take care of that if you want to apply this through pre-processing of the appropriate pre-processing of the data. But having said those disadvantages, it has advantages also. Non-iterative methods, analytical method, and that's why as a machine learning engineer, whenever first choice would be if it can be solved using normal equation. If it is, go ahead. And I am telling you, if the features are in the range of 10, 100, 1,000, even 10,000, maybe 15,000, it's fine. You can, today's computational machines can easily figure out the matrix inversion for those dimensions. It's not a problem. So please use this. So I think that's all I wanted to communicate in this lecture. And now, next, what if I have really large features, like millions features? Then none of this method will work. So how to actually solve those kind of problem will be the focus of my next lecture. Till then, stay safe. Bye-bye.